Thank you very much for inviting me in Barcelona, one of my favorite cities. And for Barcelona, we jump into Lausanne, where I live and work. This is the Olympic Committee building with the Olympic rings. And I'll start by, citing the Olympic motto, which is Citius, Altius, Fortius in Latin, and their translation applies very well to systems on chip. That's the system on chip motto. Citius, faster. We want to have higher performance. Altius, higher. We want to go 3D. We have to go 3D. Fortius means stronger, so do effort with less energy. Actually, this is the hardest challenge that we have. Now, what do we have ahead of us in terms of hardware and system design? Well, mainly artificial intelligence and machine learning. AI, ML, data-driven science require large storage space and large amount of energy for doing the computation. So we need to rethink architectures, circuits, devices. Do we really? We want to enable AI, ML on edge devices, and also we have to curb the energy consumption. The picture on the right actually shows reactor number 3 from 3 Mile Islands, which is going to be put back into operation just to feed a data center for Microsoft, which basically gives a measure that one data center, a modern one, will require a nuclear reactor. So thinking of how many applications we have in AI, ML, we may actually be out of control in terms of energy that we need. And so we might, on one side, think about what are the human and planetary dimensions of AI and ML, maybe thinking better. But this talk is not about AI and ML. And otherwise, we have to think of what we can do with the technologies that we have at hand. So if you look at the future of computing system design, you look at design, how design is a process, how we come up with chips. That's a cyclical process. We apply techniques like synthesis, physical design, verification, and we iterate in a circle, and circles are part of the theme of this talk. We iterate until we have design closure. We all know that design closure is the most important thing in chip design, but what happens if we don't have closure? And it's obvious because as we actually have more and more performance requirement under energy consumption limits, at some point we will not be able to close the loop. And we have to do something different. And that's where actually emerging technologies, new architectures, new devices are the instruments to go beyond the limits that we have today. And so we have to reinvent design in different directions to achieve the goals that we have. So if we look at computing in the era of AI, we need actually a rebirth of computing, and design automation is the enabler to do that. Actually, this is just to explain the title of my talk. I tried to make it a little bit catchy. I was talking about the phoenix. The phoenix is this mythical bird that was supposed to live in Egypt, Saudi Arabia, Persia, and it's a bird that would die and then will reborn from the ashes. And so in this paradigm, I think that the phoenix symbolizes the design of the new systems that will be different from the one that we have today. The new system will involve new technologies, new operation paradigms, but that will be done through the use of current computers, through the use of current design tools and methods. That's what I mean by the phoenix. But the technical point is not enough when we think of the future of computing systems. We have to think of our planet and its limit, look beyond technology, because advanced design and manufacture requires a plurality of skills, efforts, and geostrategic components. To make the long story short, most advanced design are done in the West. Advanced fabrication is done in the Far East. EU lithography, extreme ultraviolet lithography, requires machines that are made in the European Union, in the Netherlands, by SML. And we need a collaboration of these countries, of the corresponding people, in order to have a future for computing. So the global politics and global economics will be a key player in advancing the computing systems that we don't want them to be stuck at the level in which they are now, which is not sufficient for the new paradigms that we have in software. I will also bring my thoughts back to Japan and to rebirth of Japan after the war. There was a phoenix there too. And I'd like to mention Konoshuke Matsushita, who was the founder of Panasonic. And Panasonic actually brought to Japan all the gadgets and all the electronics after the war that made Japan rich. He used to say, peace and happiness through prosperity. Buy my items from Pioneer and you will be peaceful and happy. And his say actually was also changed a little bit into the words peace and progress through prosperity. The three concepts are highly related. Again, you can see a circle, you can see a circular dependencies among these three P's. Peace, prosperity, progress. So that's why I would like to make my first statement as follows: progress through peace and prosperity. Because we are at an inflection point where any major improvement in computing systems requires a big step. It requires peace and cooperation. These are essential because the pool of talents worldwide is limited. We would like to pull together the talents in design, in manufacturing, and we need a very wide market in order to support advanced manufacturing. Very often, there are new ideas on devices, on processors, and people will tell you, we'll never make it. It costs too much. Well, the cost in electronics depends on the volume that you are producing. And having a large volume is an enabler to go forward. And of course, probably here I'm preaching to the converters, so funding computing research generously is crucial. And as a message for Europe, we need to support engineers with good rewards, with good salaries, to retain them, to make sure that good engineers stay in engineering and produce something newer, something better. Now, I'm going to switch gears. I want to talk a little bit about the circles, the inner circles of computing. I'll use this nice picture of Charlie while he's inside the machine in the movie Modern Time. So where are we today? We moved from FinFETs to nanowires to nanosheets. That's where we are now with technology. And we can say that today the entry node is in production. Interesting enough, Apple buys most of the production from TSMC. And so this process accelerates up because there's this big need in cell phones. The N2 node is in production, will be in production in 2025, that is this year. And that will lead either a 15% improvement in performance or 30% reduction in energy consumption, which is what we are most interested in. And now we're already talking about the A14 node. So we are switching from N nano to A angstrom, 1/10 of a nano. And the A14 node is actually slated for the end of 26, which is next year. We go to new structures like the fork sheets. And here you could see the transition from the FinFET to the nanosheets. The fork sheets that are in the middle eventually will go to the CFETs, where we'll have N transistors on top of P transistor. This is a roadmap coming from HiPEAC. And you can see that as we go forward over the next decade, we'll have technologies that will lead us to a smaller and smaller footprint so we can pack more transistors, but the box will be higher. We move in the third direction, and so wiring will be even more complex in the technologies to come. So there are plenty of discussion whether Moore's law will survive, will not survive, when we will stop. According to this picture, we will not stop for at least 10, 15 years. But are there alternatives? So will post-CMOS technology be always the technologies of the future? I don't believe that. I think that some of the technologies that are alternative to CMOS are there. I'll show you this picture. That's a RISC-16 processor done with carbon nanotube technology. So this is carbon electronics. You get carbon nanotube dopes so that you can have P and N transistors, so you have complementarity, you have low power, and you can actually build it by stacking different layers. Actually, besides using a different process to do this, this was done by Analog Devices together with MIT and Stanford, then the interesting thing is that you can make many layers. This chip was done over 5 layers, and the ability of making many active layers is due to the fact that in this technology, the temperatures involved are much lower than in silicon. And we all know that it's very difficult actually to have the so-called sequential integration in silicon with transistors on top of transistors. This is the follow-up. This picture actually comes from my good friend and colleague Subhashish Mitra at Stanford about the next project. Here you see various layers combined together to make a cube where you have both computation and integrated storage. And this is kind of a key to achieve 100 to 1,000x energy delay product benefit. So this gives an idea how things can be different. And this brings the problem to discussing diversity, where diversity fits. Barcelona is the city of diversity, and it's wonderful. And this is about diverse architecture. That's the Sagrada Familia that we have, where you have a collection of structures that are fairly different in terms of materials and shape. Would this paradigm apply to system on chips? Yes, it does, because I do not think that CMOS alone will last forever, as well as I don't think that there will be a new technology that will supplant CMOS just because of all the investment that we have done. But there is a plurality of technologies that may help making silicon, making CMOS better, because they are well geared to accelerate some specific computation or communication primitives. So the world of computing will be heterogeneous and diverse because we will use parts done differently to achieve the overall game. When you cannot close the circle within the silicon, you will use the wild card to bring in a new way of doing transistor and operating them. So some examples here. These are, again, carbon nanotubes coming from an MIT. This is PCM, phase change memories, put on top of silicon, that's IBM. This is an optical accelerator for AI that does matrix vector multiplication in an efficient way. This is a circuit that would do a similar thing for machine learning, but using MOS2. MOS2 stands for molybdenum disulfide. This is single-layer electronics where electrons are confined in a thin channel, and therefore you have better performance and lower consumption than the group of Andras Kish at EPFL. And here you would have a superconducting circuit done in Lincoln Lab. So let me make a little bit of the tour on one of these technologies. I will take the last one, superconducting, and I will go to the cryo world. The cryo world is depicted here by an image that I took in the Arctic Ocean a few years ago. And I said that to talk about those technologies that operate at low temperature. Fortunately, the Arctic Ocean is not that cold. But here we are talking about operating close to 0 Kelvin or 4 Kelvin for standard superconductors. Why would you do that? Why would you go down to those temperatures? Efforts have been done in the past to chill CMOS to 79 Kelvin, and you get much better performance for CMOS. But going down to the superconducting threshold has two major advantages. One is that resistance goes away in wires, so the RC delay washes away. You don't have to deal with it. The second one is that you can compute with pulses. Pulses carry a limited amount of charge. A pulse is a logic 1, and no pulse is a logic 0. These pulses are quantized because of the quantization of magnetic fields in the superconducting domain. And so the typical standard pulse will be like this, of about 2 picoseconds and 1 millivolt. The area under the curve is quantized, and actually the voltage times time gives something in the dimension of a flux. And this flux would be 2 times 10 to the minus 15 Webers. So we operate like this, and that's extremely efficient because there is a small amount of information that you carry around on your physical layer. You can still compute with classic techniques, with classic logic. You can have computation that is much faster than we have today. And there are many ways, actually, of implementing it. Here is a chip designed in Korea. This is one done in Japan with even a more advanced technology that uses adiabatic computing. So the notion of adiabatic computing in the superconducting domain brings actually the power to a much lower value. And interesting enough, these circuits can be natively abstracted as achieving the majority function. This picture has some performance value. I like just to focus on the column on the right that gives the area delay product. And you can see that the families in the middle, the SFQ families of superconductors, have an EDP which is much less than conventional CMOS. And if you compare it to the adiabatic is even much less. And start getting into the ballpark of what is the physical limit of computation. So in summary, this type of technologies can be a support for ultra-fast acceleration to enhance AI, ML engines. It has low power operation with a caveat. You need to build a refrigerator, and you will spend a large amount of energy into cooling these chips down. It can work also as a bridge to quantum computing because of the proximity of temperature. This superconducting circuit can be interfaced between the host and a QC chip. But they also need a new set of EDA tools. And I said EDA is the key to the revolution, is the key to bringing new devices, new technologies into the pictures for doing the design. So superconductors actually can give us one step further. We can go further on in searching for doing performance at low energy, achieving performance at low energy. But if you want to go faster, you have to change the rules of the game. And that's Pablo Picasso, 1907. He changed the rule of the game in painting because he designed the faces of two models with a decomposition in their face that at the beginning was considered ugly, but in the end it was really the beginning of the Cubist movement. Now in quantum computing, there are two facets of the computation. On one side, there's the physical world with all types of devices where we use matter to do the computation. And today, there is not a consensus of what is the best technology to do quantum. There are various vehicles to perform quantum. But we should not forget the computational effort to get the computation done. You have models, you have algorithms, you have flows. You have to map them to quantum circuit. This is the quantum compilation aspect. This is the equivalent of compilation for instruction set architectures, even though it's different. And this is a very important part of the pie. That's why quantum computing does not belong only to the physicists, but also belongs to engineers and computer scientists. So the complexity of the software parallels the complexity of the hardware. It's difficult to actually develop parallel algorithms. And then you have to map this computation into reversible circuit. Reversibility is a must because nature and the natural phenomena that we use in quantum computing are reversible. And so we have to make logic reversible, which is much more efficient than irreversible logic that we have in CMOS. Biggest problem that we have ahead of us is the evolution going from noisy intermediate quantum computers to fault-tolerant quantum computers. And this type of computers are relevant to different type of applications. The current computers are relevant for doing computation in chemistry, in physics, but if we want to solve combination optimization problems, we do need to have fault-tolerant computing because every bit counts. So what's the bottom line? The bottom line is that quantum computing will be a success. There will be customers enough to sustain quantum computing, but it's not a panacea. It's not going to solve all the problem. It's going to be applicable in some domain where you can speed up the computation by having superposition and exploiting entanglement. That's a nice picture of the quantum computing from IBM. It reminds me, even though it was many years ago, a talk by Ken Olsen. Ken Olsen was the CEO of Digital Equipment. And in 1977, he said, I don't think that anyone would like to have a computer in their home. He was wrong. Actually, IBM came out with the PC 3 or 4 years later. And today, we have all kinds of computers and toys and gadgets with electronics, with the power of a computer in our home. And that's why also why digital equipment went down the drain through the 90s. But the question is for us to see what the future of quantum computing will be. That a device on a network for the Microsoft, the Googles, the Amazons, or will be that a device that can be in the enterprise, that can be time-shared among engineers and scientists? Or would that be miniaturized to the point that we will have it in our home? I have no clue of what the answer is, but actually the global outlook of quantum computing is important. I will actually like to discuss with one slide something about thermodynamics, because this is driven by the consideration of superconductors and quantum computers. What we are doing, we are searching for efficient computation. And we see that on one side, we use reversibility of quantum computers. On the other side, we can use adiabatic computation. So these are important properties. Mechanical engineers who work on thermodynamics in the 1800s actually studied profoundly the thermodynamic cycles. And what we have in computer is also a thermodynamic cycles. We create order among data by just burning energy that is dissipated within the integrated circuits. So that should be a concern to us. And the unfortunate point is that the state of the art is that we are thousands of orders of magnitude away from what is the best possible design. And that's not the case in the case of thermal machines. Even for CMOS that we have today, the limitation of data centers, of processor, is often the thermal limit. You cannot heat the chip beyond a certain amount. You cannot actually ask the chip to do too much. Otherwise, the energy cost will be too wide. And within this frame, I'd like to mention one of the projects in EcoCloud. That's the center that I'm directing at EPFL. And the idea of using actually some sort of circular model. There's a rack of chips, processors, data center. These are water-cooled. The hot water comes out of the chip, and then it goes in the turbine. And this turbine will create energy that could be put back into the cycle. Of course, the energy produced is much less than the one that is consumed, otherwise would violate the second principle of thermodynamics, and that's not what we're up to. We will never be able to do it. But that's a very interesting proposition. Again, the phoenix actually gets energy by being rebirthed from the ashes. Here we use the leftover heat of computing to create some more energy. And I found that interesting. That's not my project, but it's a project of colleagues. So this leads me to my second point in the talk. It's important to exploit the diversity of architectures and devices, because the competitive advantage of emerging technology comes from adapting the computational model to the fabric that we have. And designer accelerator is going to be the hottest topic in the years to come, either by using silicon FPGA technology or using other, more exotic technologies. But they will be applicable both in the cloud and on edge system. And it will be interesting to see what's the effort that we have to put in order to enable successful diversity within chips. And we need thinking in a different way. And we need also to be able to adapt and create new EDA tools. And that's one of the challenges for the years to come. I'll come now to the last part and maybe more technical part of the talk, which relates to modeling the common traits of computing system. So the idea is that new logic, new transistor, new architecture will use some of the same basics that we have been used today, and we have just to think deeper and go into that. Well, this is an ancient computer. This is Babbage differential engine. So I don't think that what I say applies to this type of mechanical computing machine. But still, it's a nice picture, I would say. So we search for common models, and we want to exploit our expertise in contemporary logic design for the new technologies and new paradigms. This brings us to this thought. We know a lot about logic networks and synthesis. And some people tell me, you should stop. We know enough. We have enough tools. Should move to something else, because we know how our community is. People will just often fly from one tree to another one, maybe in the search of the phoenix or in the search of something that is more rewarding. But the reality is that there is more that we don't know as compared about what we know in logic. That is true. And the question is that relevant? I believe that that's relevant, that we have to dig into the far side of the moon, because there are techniques that are methods to solve difficult problems that can be enabler for the new technologies. And we cannot miss the mark by just saying we are satisfied with what we have today for digital design. So the basic model, the logic networks, you have primitives that are connected. You know, in the beginning, you have just NANDs and NORs connected. The data structure that's most used today is the end invert graph, as proposed by Mishenko and Brayton. There are some other models. Optimization with this graph, with this model, is computationally intractable, as it's very well described in volume 4A of the Art of Computing Programming, the book of the good Donald. So let's talk about other models, like majority logic synthesis. This is an alternative model to do AND/OR logic. This is something that was studied in my group for a while. It was not something new. People studied majority in the 60s, but it was not studied as a method to do EDA, to make design algorithms and design tools. It was studied per se. And in majority logic, a gate has an odd number of inputs and will be true if the majority of the inputs are true. This can be formalized by an algebra with its statements. The algebra can be shown to be sound and complete. So it has the reachability property. So you have a design which is in one configuration, and you would like to go to the best configuration. There's always a path done with steps that can be described by these atomic axioms that will take you from where you are in the design to the best design. Then this path can be difficult to find, can be of a length which is over a polynomial. The problem stays hard, but this algebra gives you potentially the possibility of reaching the goal of achieving optimality. And the underlying representation is this majority inverter graphs, where you have majority gates, in this case 3 majority, and bubbles that are inverters. How do you optimize it? Many flavors. You can do it with algebraic rewriting. So you will use rules derived by the axioms that will let you go from one configuration to another configuration. But you can also use Boolean methods. Boolean methods exploit don't care condition, exploit resubstitution, and basically leverage the fact that the majority operator per se has some redundancy built into. So if you simplify a part of the network by making it faster and slimmer, and you create an error, then this error may be compensated by other parts of the network that feed in that majority gate. So you have this important potential. Overall, majority has shown that can improve delays in CMOS by 15 to 20%, so it's highly desirable as a way of processing logic. And it's also very successful for logic where majority is the inherent model for the technology itself, than in the superconductors, logic in memory, and also all kind of optical logic relies on majority logic. As I mentioned, superconductors, let me say something about that. You know, what's the key difficulty in optimizing them from the logic point of view? The first problem, you have these pulses. These pulses are tiny. So it's hard to handle high fan-out. And so you have to use splitters to multiplicate these pulses around your chip in case of fan-out. The other one is that the pulses have to arrive at the gate at the right moment. This is highly pipeline logic. And you would see a circuit that is on the right part of the picture here. You will see the bubbles in yellow that represent the information. You want the bubbles to arrive at the gate more or less at the same time, or anyhow before the clock that triggers the computation. This forces us to introduce buffers or delay elements. Here you have one rectangle in blue that can be seen as a D flip-flop that actually is there to delay the passage of a pulse to put it in line with the other ones. Now, if we go to the example of adiabatic logic, which is extremely nice because it's low power, it leverages majority, then you have the combination of applying majority rules for optimization and doing this buffer and splitter insertion. The problem in this logic is even more complicated because the splitters are clocked. So every time that you insert a splitter, you have to think of the balance. And I don't want to get into the description of this intractable problem, but just give you an example of what happens with a full adder. Here you have a full adder in its the raw form, realized by some majority gate. Here I'm putting some boxes as a splitter, and here you put the buffers in order to synchronize the circuits. So in order to make this technology working, you need to have tools that deal with this. You also need to have good tools, because if the tools are not good enough, you will end up building chain and chains of buffers and will make the logic inefficient, and eventually you will end up consuming more power than needed. Now, I would like to make a point of two properties of logics that are important and often neglected today. The first one is on the role of linearity. We deal with AND/OR logic. We tend to think in terms of AND/OR, NAND/OR, and these are nonlinear gates. Majority also are nonlinear. XOR are linear. The only problem is that you cannot build everything with XORs. You cannot build other with XORs. You need somehow some nonlinearity in order to get the computation done. But it's useful to decompose logic graphs, to expose the linear and the nonlinear part, because properties are associated with those two parts independently. And this leads also to the notion of this other graph, which is the XOR majority graph, where instead of having inverters, you would have XORs. By the way, you can think of an inverter as an XOR that has one input. And these networks are interesting because of the self-duality of the XOR and majority. Self-duality means that if you flip the inputs, then you also flip the output. So that's, as a result of this property, you can have that XORs and majority gates can quote-unquote commute, or XOR can flow through the majority. You will see here a transformation on the sketch that shows how aggregates can be realigned. Now, I'm showing this because there is a very strong connection between device and emerging technologies and this type of models and their applications within logic. And the old story actually goes back 15 years ago. Some of the work was done in my lab with the design of polarity control transistors. These are transistors with two gates. And one gate will make the transistor either P or N, so you have one type of device. This actually is silicon that implements that. But I don't want to talk about device. I want to show you some gates that can be realized in a very compact way. And you can derive in a compact way the exclusive OR and the majority gate out of this transistor. So when that work on devices and transistor was done, then there was the issue of how do you design with them? And actually the result was to design with majority and XORs, or with majority and inverters. So the majority-based paradigm came out of the need of a new emerging technology. And this is nice because actually puts us back in full circle. We had CMOS, we go to a new technology, we develop EDA for this new technology, and then we find out that this new technology is also good in the case of CMOS, and today majority logic is used a lot in CMOS design because that's where we do actually the large design. For emerging technology, it's difficult to say how good it is because we don't have realized benchmark circuits, but it's still very useful. The last topic that I would like to address is the multiplicative complexity, because it's a property of logic circuits that has ramification in encryption and in quantum computing. So starting from our graph, now we have a network model that has XOR and AND. So again, we separate the linear from the nonlinear part. And that's interesting because that's an abstraction of computation. You have a data flow where you have addition and multiplication. You can get a skeleton in terms of a Boolean network that has these gates. And the multiplicative complexity is defined to be as the minimum number of ANDs that you would need to implement a logic function. Obviously, given another function, there are many ways of implementing it. So it's not just a question of counting the number of AND gates, you have to count them over all the possible implementation. And here you will have one example where you have the majority function implemented with 3 AND gates, so the structural computational multiplicative complexity is 3. On the right, you will have the same logic function implemented with 1 AND, which is the minimum number of ANDs that you need in order to majority. And so the multiplicative complexity of the majority function is 1 because it's the minimum. And finding it, it's a hard problem. It's known for functions up to 6 and for some other functions. But it's an important concept, as we'll see in a second. And along with that, it's important to compute the multiplicative depth, which is the longest path of n gates. And because the depth and the complexity will relate back to properties in design. Let me give you the first of the two examples that relates to fully homomorphic encryption. This is an extremely important problem today. Because of privacy, we like to do computation done on encrypted data so that nobody actually can have access to the data while it's flowing through a computer. Now, the speed of the computation is essential within FHE, because if it takes too long to do a computation, we wouldn't care and we'll take the risk to just compute with the raw data. So the idea is to use logic synthesis to restructure the computation. And you want to do that by restructuring the skeleton of the networks in terms of n and XOR gates. The n represent the multipliers. The multipliers in FHE generate noise. This noise is there to protect the information, but the noise should not go beyond a certain level, otherwise we will not be able to recover the data. And that's why in FHE you need a step which is also computation expensive, which is bootstrapping, actually, to clean up the signal. So key metrics in here are reducing the multiplicative complexity because it's related to the noise and to the depth. And there are various research there that actually affect new metrics. One of that is called MC-aware MD optimization, where you have an objective function, MC times MD2 squared, that it's there to optimize the end part of the computation. And another technique that is important is the ease of balancing. That is, you have this XOR, and how can you balance them in order to give you a better computation flow? Last example is using this XIG graph, XOR n graph, in quantum compilation. What is the problem? In quantum compilation, you take an algorithm, you want to map it into reversible logic, and then use a library. A typical library that's used is the Clifford plus T library, where you have these T cells that are more expensive than others. Well, of course, this can depend on the technologies, but the T cells, which are a pi/4 rotation on the Bloch sphere, are not very desirable gates because it requires more time to implement them into a quantum computer. Now, the interesting thing is that if you model the combinational logic blocks in quantum computation, which are called quantum oracles, and these are present in many algorithms like in Shor's algorithm, then in there, the multiplicative complexity of these blocks relates to the number of n's that you have that then can be implemented in terms of Toffoli, and there's a bound that actually says that you can implement it. It's at most 4 T cells per n that you have. So restructuring the computation, the quantum computation, by using the multiplicative complexity as a guideline will actually lead us to create circuits that are less expensive in terms of the realization as quantum computers. This leads me to the last statement in the talk. Logic synthesis is a root of computing, is a very important topic, still unexplored in part. Most computation can be abstracted by graph models, and logic synthesis actually enables optimization of these graph models. Some approaches can be shared among technologies that are inherently different, like minimizing critical path, like minimizing some types of complexity. And in particular, multiplicative complexity is key to solving various problems, as we said in the case of encryption and in the case, for example, also of quantum computing. This leads me to the final conclusion over these talks, I covered a lot of ground, so I'd like just to summarize what I think it's important to keep in mind. First is that progress requires stability, requires international collaboration. This is what we have to do as scientists, engineers, especially in our messages to political leaders. It's extremely important for the evolution of computing system. A better tomorrow is linked to better computers. Better computers cannot be done if we don't work together. Efficient computing also needs a match between architecture and technology. So accelerators are key to diversity, to have new parts that can speed up the computation and or make it more energy efficient. Logic modeling is a fundamental tool. Most digital chips have a large part that does combinational logic, and this has to be addressed with models and, again, understanding diverse design, diverse methods, making mix and match of techniques is extremely important. And finally, chip design is entering a new exciting epoch. Because of AI, ML, there will be more and more needs of chips. And this is extremely important to be able to design them effectively for supporting the fast evolution of algorithm software, systems, services that we all use. So thank you for your attendance. Thank you to my sponsors. Thanks to my graduate students that, as a big group, are here at Stanford under an semicircle, a half circle. And finally, this wonderful picture of a circle of snow at EPFL. Snow was falling on top of the library that has these circular holes, and here the snow falls on the ground. So thank you again.